Do you ever wonder why you'd fall over while you're riding a bicycle or a scooter? Well, that's because of the turning effect of forces.
The turning effect of forces has two other names, torque and moments, all of which mean exactly the same thing. Moments are calculated by this formula, F times d. F is the magnitude of the force on the body in newtons, and d is the perpendicular distance between the line of action of the force and the pivot point in meters. Together, it makes the SI unit Newton meter. Now what is the line of action and the pivot? We'll come to that later. But first, the magnitude of the force. Let's say we have this orange box of weight 50 Newton on the plank here, which is balanced on the green triangle. Since you know the weight is 50 Newtons, then the magnitude of the force is simply 50 Newtons. But we also have to take note of the direction. Weight is the gravity acting on the box, so it goes directly downwards.
In this case, if you follow how the plank turns, you will notice that it goes clockwise, so it is a clockwise moment. Then, since weight is acting directly downwards, its line of action is a vertical straight line. Next, to know where the pivot is, it is the point around which the body, in this case the plank, revolves around. So, it is the point that does not move as the body revolves. The perpendicular distance will just be the distance at a right angle to the line of action to the pivot point, which in this case is 4.5 cm.
Now that we've given you a brief recap of moments of forces, let us introduce you to the phenomenon that we will be explaining. What do you think will happen when he turns?
In the situation of the scooter, the pivot point is at the base of the wheels, because this is the point where the whole scooter revolves around. The CG is approximately in the center. When the CG is moved due to our body movements or weight, it falls and creates an anti-clockwise moment which causes the whole thing to fall over.
Why? This is due to the gyroscopic effect. If you recall, at last year's school carnival, there was an odd spinning red wheel. That was a gyroscope. A gyroscope is a device that can be used to maintain orientation based on the principles of angular momentum. It is a mechanism by means of which a rotor spins around an axis.
The gyroscopic effect can be best explained by the principle of behavior of a gyroscope. Pretend this wheel is the scooter's. According to the equation that describes gyroscope behavior, the torque on the gyroscope applied perpendicular to its axis of rotation and also perpendicular to its angular momentum causes it to rotate about an axis perpendicular to both the torque and the angular momentum. This rotational motion is referred to as precession. If a spinning gyroscope is placed such that its axis is horizontal and loosely supported from one end, the gyroscope does not fall, such as in the scooter. It rather maintains its horizontal axis, and the unsupported end starts moving in a circular manner about the horizontal axis.
However, due to precession, when another force is applied to the wheel, such as when Verdun attempts to turn the scooter, the wheel does not immediately spin in the direction of the force applied. This is why Verdun lost control and fell. A gyroscope can be considered as having three axes, as the spin axis is the one defining the gyroscope strength. If the spin axis lies along a vertical line, the other two axes lie in the plane of the page. The gyroscope spins around its spin axis. Torque is applied to the primary axis, and the secondary axis is the axis of precession. The spin axis gives rise to the gyroscopic effect.
Another example is the compass in your phone. Do you know how the screen rotation function works? It is due to the gyro compass inside your phone, which is an application of the gyroscopic effect. It uses the effect of gyroscopic precision and is also used for navigation on ships. It is a spinning wheel mounted on a gimbal. The wheel's axis can orient itself in any way.
Now that you have learnt about this phenomenon, we shall move on to our second topic, magnetism.
This is another pivot system. If you place the bar magnet at this end, an anti-clockwise moment is generated. If you place this star magnet, north pole up, on the other end of the ruler, the system still remains unbalanced. This is because the bar magnet has a greater perpendicular distance, and as such, a net anti-clockwise moment will still be generated. We can overcome this by increasing the downward force on the star magnet. This is possible through repulsion. As we know, like poles repel, so if we bring this north pole to the star magnet, it repels and moves downwards, bringing the system to equilibrium.